Yeah, what is that for our?
Oh, I got it.
That, we would be 11.
Oh, yeah, 11.1.
Because in time is BC time, right? They're an hour behind us.
Okay.
So, I really empathize with you. I do. It's tough being put in a situation where there's an individual who would like to go over the same information but in a very specific way. And the way that I would go over stuff and the way that somebody else would go over stuff is maybe a little bit incongruent, and so it's hard to understand. There are 4 ways of communicating enthalpy changes for a given chemical reaction. We could talk about any 4 of these things if we wanted to, but we're going to kind of go in order. Stating the molar enthalpy of a reaction. That was kind of the first one. And these are, so I've got some kind of pre-written out notes. Now, I'm not asking you to write all of this stuff. I don't really care what you write down. I'll put a caveat on that. I do care what you write down, but I want to go over this just for our understanding. So when we look at this, okay, tell me, what does this mean? Do you remember what all of this stuff means here?
Enthalpy change.
So this is an enthalpy change, right? H is enthalpy change. And this is a combustion reaction, right? So we're talking about the molar enthalpy of combustion under, and then the not, the little degree sign, that just means under standard conditions, under standard ambient temperature, pressure, that kind of thing. So the molar enthalpy of combustion for methanol is negative 725.9 kilojoules per mole. Whoa, I don't know what all that means. Is that for every 1 mole of methanol we burn, we release 725.9 kilojoules of energy. What if we burned half of a mole of methanol? How much energy would we give off?
Like 360.
Yeah, you know exactly what's going on. It's half of this, right? So if that's the molar enthalpy and we burn half a mole, then it's half of the molar enthalpy, exactly. What about this? This is the molar enthalpy of formation. And remember, formation is a very, very, very specific reaction. So the formation of methanol is you take 1 carbon and you take 2 hydrogen molecules and half, what we call half of an oxygen molecule. We'll kind of go over that a little bit later. And boom, all of a sudden you make a methanol molecule. So what that means is, sorry, are we releasing energy or absorbing energy by having this reaction? Releasing. Our system, remember, this molar enthalpy refers to, is the system gaining or losing energy? If the system is losing energy, then what's gaining energy? So yeah, whatever is around it, right? It's surrounding. So if it's aqueous, then the water is gaining the energy. If it's not aqueous, then yeah, it's the surroundings, whatever it's in contact with. So 239.2 kilojoules are released when 1 mole of methanol is formed from its elements. I don't know. Is this fairly straightforward? I can just list off the molar enthalpy of a specific reaction. And then as long as you know the moles, the number of moles of something reacting, then you know how much energy will be given off, just because you're using unit analysis. Is this relatively straightforward? Yep, okay, all right. The second way that we can communicate enthalpy changes. So the first way, I could just tell you the molar enthalpy. The second way I can communicate an enthalpy change to you is by having the enthalpy change for a very specific reaction, but just off to the side. And you see this a lot. You see this really, really often. If I were to just bring up any old diploma exam, so just casual reminder, you can search up diploma exams by just searching up diploma exams. Writing diploma exams in Alberta, and when you look up Chemistry 30, sure, let's choose the 2017 one. Oh, whatever, it doesn't matter. Buffering. Perfect. So when you look at this, see, I just went to any old random chemical reaction, whatever, doesn't matter. Don't look at the question. Look at the equations. Describe for me what's going on here in equation 1. It's a combustion reaction. And what is the enthalpy of this combustion reaction? 1,234.8 kilojoules. Now, when I combust this particular chemical, does this system release or absorb energy?
Release.
It releases. So it's going to make its surroundings what? Hotter or colder? It's going to make them hotter, right? That's all. This is one way. This is one way for me to communicate an enthalpy change. And you have to know that this means that 1,234.8 kilojoules are released for every how many moles of ethanol? 1 for every 1 mole of ethanol. Okay? If I were to double everything in this chemical reaction, if everything got doubled, what do you think should happen to the enthalpy? It should double as well, because if we have twice the number of chemicals reacting, twice the number of molecules, we're probably releasing twice the amount of heat or energy. Does that make sense? Yeah, okay, so this enthalpy is specific to this one chemical reaction and no other chemical reactions. Okay, so as by way of an example, this chemical reaction, the reaction is exothermic because it's releasing energy, and it's releasing 128 kilojoules for every 1 carbon monoxide, sorry. Do you have a little bit of room to write another chemical reaction? Yes. Yes. Okay, let's. All right, let's do it. Doesn't matter. Howdy, sir.
Howdy, Walton.
Now, this is the exact same chemical reaction, except I'm going to change the coefficients. I would like you to tell me what is the enthalpy, the standard enthalpy of this reaction going to be? No, I'm not. It's not a trick question, is it, Mark?
Negative. Yay, -2. Kilojoule.
Is this like? Does that kind of make sense?
Yeah.
If you have half of the chemical amount reacting, then you will release or absorb half of the energy. Okay, all right, no problem. So that's 2 ways of communicating enthalpy changes. I could have said the molar enthalpy of the reaction is this, or I could have said that the enthalpy of the reaction of this specific reaction is this. And that's totally fine. It doesn't. It's kind of the same thing. Okay, perfect. Let's move on. So example number 4: sulfur dioxide and oxygen react to form sulfur trioxide. The standard molar enthalpy of combustion of sulfur dioxide in this reaction is negative 98.9 kilojoules per mole. Blah 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 blah. What is the enthalpy change for this reaction? So Did you write down a balanced chemical reaction for this? Yes, you did.
We put half an oxygen. Yeah, we did half.
Okay. So that's totally fine. What I did here is I wrote down that for when you have SO2 reacting with O2 to give you SO3, SO2 only has to react with half of a molecule of oxygen to make SO3. And you often see this in the energetics unit. You often see fractional coefficients. When's the last time you saw a fractional coefficient? Probably never. Probably never. Maybe you saw it in grade 9, but just as an example or something like that. So this is typically not the way we would write a lot of chemical reactions. We usually want to use lowest whole number coefficients, right? Talissa, do you mind shutting the door? But what I want to say about this is that this chemical reaction has an enthalpy of negative 98.9 kilojoules per mole. So how did I get from here to this chemical reaction? What did I have to do to everything? I just multiplied everything by 2. So does it make sense that the enthalpy of the reaction also doubled?
Yes.
Yes, okay. Another way of saying that, I'm going to erase this, is that the enthalpy of the reaction, if every 1 mole of sulfur dioxide releases 98.9 kilojoules, but in this particular reaction we have 2 moles, all we have to do is use unit analysis in order to identify the amount of energy released. And so if normally you would have 1 mole releasing this much, well then 2 moles will release double that amount. Like, can you see how there is an intuition way of doing this and then there's a unit analysis way of doing this? And both of them are equally valid? Okay, no problem. All right. This is a big one. This is one that I really wanted to focus on. Enthalpy changes can be written as either a product or a reactant. Now, what I want to ask you is if an equation has an enthalpy change of plus, 1,344 kilojoules. What I want to know is this reaction releasing energy or absorbing energy from its surroundings?
Absorbing.
It's absorbing energy from its surroundings. Now, let's try and think about this. If I had a really simple reaction, if this reaction was absorbing energy from its surroundings, do you think that energy component, think back to the equilibrium unit, do you think that the energy term should be a product or should it be a reactant? Let's use your intuition. Where do you think it should go? Product or reactant? Product. Sure, no problem. So, Matthew, thank you for contributing to the class by apparently answering the question without looking at the question. Okay. So when you see an enthalpy of positive 1,300 kilojoules, you know that this thing is absorbing energy. But then when you see a reaction, and I say, oh, positive 1,300 kilojoules, well, this reaction doesn't look like it's absorbing 1,300 kilojoules, does it? It's releasing 1,300 kilojoules. So if you ever see a reaction that has energy in the product, it must be releasing energy, right? So instead of putting it here, where would we put it? Does that kind of make a little bit more sense? So the system is consuming 1,300 kilojoules for every one of these, or every two of them, or whatever, that kind of thing. Now, what I want to bring your attention to is, let's change this to a negative. Is our system releasing energy, or is it absorbing energy? Okay, so where should the energy term go? On the product side. And it should it be positive or negative? This should be positive. I'm curious, why? Why should it be positive? Max?
Because if we use Le Chatelier's principle,
Okay.
we can have the negative on the left, and then it makes sense.
Oh, so if you said negative energy over here,
Yeah.
it would be perfectly fine?
No.
No.
Yes.
No.
No. I said no first. Yeah.
Because negative energy is
Negative energy doesn't exist.
Oh.
that.
Okay.
Yeah. I get it.
Yeah.
Yeah.
Okay. Th-
What about antimatter?
Point being, it's
Shut
like
up.
we're releasing energy. The atmosphere's gain.
Okay, so what does the negative sign actually mean in an enthalpy? What does the negative sign actually mean? It just, all it means is this one thing from this thing's perspective, is it gaining or losing energy? That's all it means. So this negative tells you where to put the energy, but it doesn't have to remain negative once you put it there. All this means is it going to be a reactant or is it going to be a product? Then, once you've actually used that sign, once you've taken that into context, then you don't use it anymore. If I'm releasing energy, then I must be releasing this much positive energy into the environment. You can't release negative energy. Negative energy doesn't exist. Hopefully that makes sense. So every time you see energy in an equation, you will always see it as a positive term, either on the left-hand side or on the right-hand side. So what I want to ask you is the enthalpy for this particular reaction. Is it positive or is it negative? It's positive 350 kilojoules. The enthalpy for this particular reaction, is it positive or negative? Negative. It's negative. Negative 297 kilojoules. Do you see how this and that are literally the exact same thing? It's just that the negative or the positive tells you where inside the equation should it go. That's all it is. So we have three ways of communicating energy changes, and they're all very, very similar. If we were to go back to the first way, if I'm just telling you the molar enthalpy of some sort of a reaction, right, is this going to go on the product side or the reactant side of a reaction? It's going to be on the product side because we're releasing energy, right? So all three of these ways are very tied together. They're very kind of easy to relate them to each other. And then, I don't know, did you do these examples? This is on the bottom of page 3. Yeah, you did? Okay. And did you identify them as endothermic or exothermic? Okay, so does it make a little bit more sense? Does it make a little bit more sense why we put the enthalpy on the reactant side? Yes, because the system is absorbing energy, the system is releasing energy, the system is absorbing energy, right?
Yes, sir.
So in this first reaction, in the very first reaction, is the surroundings going to get hotter or colder?
Colder. Colder.
It's absorbing energy from its surroundings, right? Both of these things indicate, or should indicate to you, that it's absorbing energy from its surroundings. So it's going to get colder, right? And equation number 2 is its surroundings going to get hotter or colder. It's going to get hotter. It's releasing energy. It's releasing energy. Both of those hopefully should make a little bit of sense. Okay, and then there was a practice diploma question. I don't really want to, or I don't really care to go over it right now. Ooh, I don't know why that's happening. Okay, I think this is where a lot of people have some big conceptual problems. Was it okay? Yeah, was this the easiest one? Really? Oh, okay, all right. Maybe, I don't know, maybe this is because we talked a lot about potential energy in the classes leading up to this. But hopefully you understand that an endothermic reaction, is an endothermic reaction absorbing energy or releasing energy?
Absorbing.
It's absorbing energy. Now, what type of energy do chemicals either gain or lose? Do they gain or lose potential energy, or do they gain or lose kinetic energy? Okay.
Potential in the form.
Okay, so yeah. I think the question was worded improperly. When I rearrange the chemical bonds between atoms, what I'm doing is I'm altering the potential energy of the system. And the only way I can really explain that is by maybe taking a look at an example. So here, magnesium and oxygen, they really want to be together. Magnesium atoms and oxygen atoms really, really want to be paired up with each other. There's actually, there's almost like a force that's drawing them together. Not really, but you can kind of think it that way. So, which side of my system has more stored potential energy? The ones where they really, really want to go together, or the ones where they're happy just hanging out together now that they're together? Yeah, this side has way more. This side has way more potential energy. I'm not saying magnesium oxide has no potential energy. I'm just saying that it's got way less potential energy compared to this. So this is way less potential energy. So what's happening is we're dropping from a level of high potential energy to a level of low potential energy. Now, if our system decreases its potential energy, does that mean we're gaining or losing energy?
Losing.
Yeah, the system's losing energy, so is its surroundings going to get hotter or colder?
Hotter.
It's going to get hotter. I don't know, hopefully that makes sense.
Yeah, it's pretty.
Okay, all right, perfect. So we can take this way of communicating an enthalpy change, and we can turn it into this diagram. Is this an endothermic or an exothermic reaction? Exothermic. Exothermic reactions, your products will always have a lower potential energy. Always, always, always. Okay? Always, always, always. Always, always, always. Here we've got an endothermic reaction, so we're absorbing energy, so we must be increasing our potential energy. So when we break these bonds and when we rearrange the atoms to make something new, we must be gaining potential energy. So what does my solution's kinetic energy look like? Is the solution's kinetic energy gaining, like going up or down? What's our potential energy doing? Is it increasing or decreasing?
It's increasing.
So if the potential energy is increasing, what's happening to the kinetic energy of the surroundings? It's decreasing, right? Something's gaining energy, then something has to be losing energy. And then this question I want us to totally pay attention to, because this is really important. This is a super duper important question. And I didn't tell Mr. Brown that this slide and the next slide are the exact same question. It's all just one big question. Okay? So I think what happened was he might have answered these slides or talked about these slides, not knowing that they were dependent on each other. So let's take a look at this. Don't read that. Talk to me about what's going on here.
The temperature is rising.
Yep, we've got a reaction. Yep. And what are you measuring here? Are you measuring the potential energy of the system, or are you measuring the kinetic energy of the surroundings?
Surroundings.
Yeah, you can't directly measure the potential energy of a system, right? But you can measure directly the kinetic energy of the surroundings. So what's happening to the kinetic energy of the surroundings? It's going up. Our temperature is increasing. So let's think about this. If the kinetic energy of our surroundings is increasing, then what must be happening to the potential energy of our system? It must be decreasing. So let's look at this. Oh, man. I thought I was going to be really quick about that. Where do we have a potential energy that's decreasing? Is the potential energy under A, is that decreasing? No, so A is out.
That's what you told me.
I know. It's okay.
What?
The kinetic energy of our water increased, yes?
Yeah.
So that means the potential energy of our system must be decreasing. Where do we see a decrease in potential energy? Is B a decrease in potential energy? Okay, so that seems pretty good so far. Is C a decrease in potential energy? Okay, perfect. So B and C we're happy with so far. D, is D a decrease in potential energy? No. So A and D are out. What I want you to look for, what is the only difference between answers B and C? The greater than and less than signs, right?
Alligator.
Yeah. I like to call it, instead of the alligator for me,
Pac-Man?
no.
That was a weird, like,
The hungry boy. A snake?
That's an alligator.
What is that?
That's supposed to be a snake.
Is that a salamander?
Hey, let's
Snake?
just let him finish. It's a snake.
Yeah, it's a
What's
snake.
cornflakes, you guys? Is it cornflakes?
It's corn.
It looks like corn.
Oh, that's my sneak.
We get a cornflake up here.
You know, Pac-Man would be a
I
lot.
think, yeah, let's get cornflake out here
Yeah,
and
Pac-Man.
show us the right answer.
Is he shooting lightning?
No, that's fine.
Why do cornflakes kill?
This is why we can't have any nice things, you guys.
Oh, I loved him.
Undo it. Don't undo it, please. Nope. No, not gonna happen.
That's hurt feelings.
You have to press it at the same time, don't you?
Yeah, I didn't know if I
you
could
could
do
go top
it.
left, that little arrow. That's like,
Whatever.
now we just have a Z.
Okay. So which one of these is more? Which one of these kind of fits our context a little bit better? B or C?
C was perfect. I'm guessing.
C? B?
C?
B? Is this a positive or negative enthalpy change? Here. This is supposed to be a negative enthalpy change, but that's not telling me negative, right? This is telling me negative, so it's got to be C.
I knew it. It's called skill.
How did I know that the enthalpy change was negative?
Because it's going down.
Because our system is decreasing its potential energy, right? It's releasing energy to its surroundings, right? So it's getting hotter. So remember, the drop in potential energy, this means it's exothermic, but then this means it's endothermic, and those two things don't make sense, right? So that's not appropriate. And then there was a bunch of other stuff. Blah 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 blah. Yeah, that's totally fine. Sure.
Let's do question.
I asked you to get some textbook questions done.
We should probably just do it. Because he like made it super confusing.
Did you want more time to do those textbook questions?
Yeah.
Yeah?
Yeah.
Okay. Jonas.
Which I got.
They're page 501, questions 3, 4, and 6. What? Oh, I didn't print off enough textbook questions? They're right here though, aren't they?
It was not enough for
You weren't here, but we're supposed to.
I wasn't speaking anything.
Yep. No, I know. That's. I have a problem. This is why I don't like using our textbook very much. The wording. Yeah, it's the wording of the questions. Okay. I only want to have to say this once.
Yes, sir.
So can I interrupt you?
Yes.
Can everybody focus their attention onto question 6A? So question 6 is asking, for each of the following reactions, translate the given standard molar enthalpy into a balanced chemical equation using the delta RH method, or notation. Then rewrite the equation, including the energy as a term, assuming water is produced as vapor. All that means is, do you see how they're giving you a molar enthalpy of combustion here? So write a combustion equation for that thing. Write a combustion equation for this substance. So what is the substance in question in the 6A? Propane. C3H8 plus O2 gas. Propane is a gas at room temperature. Gives you carbon dioxide and water vapor. So let's, right, it says write a balanced chemical equation. So what is the balanced chemical equation for this? How many carbons? 3. So how many carbons? 3. How many hydrogens? 8. So how many hydrogens? 4 times 2 is 8. Good. Now here's the problem. Have we balanced combustion reactions before?
Chem 20.
Yeah, Chem 20. It's been a while. CHO, right? CHO. So you gotta look up, and you, remember we're always balancing left side versus right side, right? So how many oxygens are on the left side right now? 2, and how many oxygens are on the right side? So I see 10. Right? Yes.
That's 6, and then 6 plus 4 is 10.
6 plus 4 is 10. So how can I make 10 over here? Perfect. So I have a balanced chemical reaction. Now what it's asking me to do is it's saying the molar enthalpy of combustion of propane is negative 2,043.9 kilojoules per mole. So what am I going to do here? Should I add, I'm not saying I have to add this term in particular, but should I add an energy term on the left side or the right side?
Right side.
It'll be right side. It's releasing energy, right? Now, this is in every 1 mole, for every 1 mole of propane, we release this much energy. How many moles of propane do we have reacting here? 1. Okay, so that's fine. I can go straight ahead and I can plug in plus 2,043.9 kilojoules. That would be the answer to this question. If I didn't have a 1 here, imagine I had a 4. What would this number be? Just whatever it is times 4. Does that make sense? Are we okay with that? So remember, that number is the molar enthalpy of combustion for propane, so it depends on how many moles you have inside your reaction at any given time. That's all I wanted to say. So continue on. What? No, you're not handing this in, but that doesn't mean don't do that.
Mine's really messy.
Yeah, that's fine if it's messy. I want to go through these questions in about 10 to 15 minutes, if that's okay with you. We're going to do a lab tomorrow.
Do we have a quiz this week?
Yeah, we do. We're going to have it on Wednesday.
Okay, where is it? It's like.
Because this is 2000. We're going to do unit analysis, right?
I'm pretty sure like
We're looking for the enthalpy of the reaction. I don't know.
We did that once with the
Yeah.
that's what I figured. And it's not.
What is my favorite? He's so funny because he was like moving up and down.
I don't know.
To yourself, but
One question. Where is it?
I don't know. I think it's one of these.
I need to find it. Some moles per second. It tells you. Okay, it might have been this one. It was like negative 98.8. 0.9 kilojoules. And then
oh no, he did.
It was like the. It was like both.
His energy belongs. Yeah.
But he
Similar proud quiz.
So especially that last question.
Yeah.
This whole process. It's one of my greatest questions I've ever written. Definitely subject your class to it.
Oh my goodness. Okay, I'll see what I can do.
What exactly am I supposed to be doing?
So it wants you to rewrite this. Yeah.
Wow. But then this one's like in here.
Yeah.
Freeze and falling down. Are you vaccinated?
Oh, never mind. No, it actually wants you to figure out. So what I want you to do is just spend this now. Let it down Yes,
Actually, no, we multiply because it's per. What?
Alright, let's go.
Okay, so you need kilojoules per mole of substance.
Oh my god.
So you have the number of kilojoules. How many moles of hydrogen? So this much energy for every 2 moles. But molar enthalpy 1.
Did you answer the first? What's the difference between a cold?
So let's do the half.
No, just do unit analysis.
Okay.
That's all you have to do.
So okay, so like this thing, cards right here. Kind of.
Yeah. So how many kilojoules are we at?
Negative 483.6. Yeah. Negative.
Sure. So the molar enthalpy of any reaction is kilojoules. So you want kilojoules, and how many moles are reacting in your reaction?
2.
Why are you happy about
Battlefield that went on
It would be more too.
If, okay, the way I think about it, if your 2 moles react, how much energy is it? I'm a speaker. Yeah. But if 1 mole reacts, that's where you, that's, like there's the intuition way. I'm just saying, if 2 of these reacted, it makes this much, then 1 is half as much, right? Or you
already.
Okay.
Barrett Getter.
and it's the
Okay.
exact same. Yeah, so this question is saying, right? Right the enthalpy as a product of that reaction. So what's enthalpy measured?
Yeah, what the? Just get all the kids back from you.
Do you know what I mean? So you have kilojoules per mole, cancel out moles and get kilojoules. Here, you want kilojoules per mole.
I'm going to all of one.
So divide it by how many moles are reacting. Yes. What does this kilojoules per mole mean? What does molar enthalpy mean? Change in energy, right? So it's the change in energy for every 1 mole that reacts.
Could you just send it to?
So here, it's all dependent on the context.
Yeah, just
Here is asking, what is our total enthalpy? If 4 moles, right? Because that's the equation. So if 4 moles of it reacts, it will
Yeah, I know.
change.
Dude, these are done.
Yeah.
It's just we have to get this.
Yeah, I know.
And they're very related to each other, right? It's just that one is dealing with the total energy change of the whole reaction. One is dealing with per mole how much would have changed.
For that what?
For that one reaction for one. And we're gonna go over all of these questions, every single one of them. We'll go over. No, I want to make sure that we're all on the same page for this before we move on. There's no point in
I'm too busy. Psychological operation.
Oh, science.
Psychological operation is where you use your intelligence to outsmart your game intelligence.
Okay. Sure.
Yeah, but these cost way more. If you resell them. How much of those go in?
I'm gonna give you a couple minutes to finish up, and then we're gonna go through these questions together. You got this. You got this all done?
No, 4. They go for
That is.
Oh, okay. So you just gotta wait more time today?
Of course not.
Then what do you mean of course?
Oh. Specific capacity.
Don't lie to me. Yes or no? Sneakers, when I'm doing you guys a favor by going over information shifts.
I will be there right now. It's almost time.
Okay.
I've never played Overwatch.
Don't let me
Like,
get
yeah.
Okay, don't distract anybody else.
Yelling at them.
Wait, that's 12 waiting. Five aside or
Wait, really?
Dude, what else is
You like to coach the team.
Like a tutor coaching a student for battle?
The whole team. Like she coaching and I'm the student coach.
So could you imagine coaching?
Yeah,
You're
so
going to just tell them to play the game.
A is just
Because you're like battle plan guys, battle plan, take cover.
So in A, it's saying what's the information? Well, now you're reached 140. You could just say like that using delta RH. So you just say delta RH is it's a very small difference between them. It's subtle.
Yeah, Overwatch 2.
It's like it's the same game. What's different? I don't know.
Okay, why didn't I learn?
Like,
Matrix.
6mm.
I just swallowed.
Is it like equivalent to like just showing like a straw?
Snapped off. It's stuck in here.
I was so trying.
But I know I take it out.
We're bad to do it.
I don't know, I'm latex.
Ow. Finger. Wait, what? You posted something? Or like oh, okay. Like manual? No.
Yeah, come. I've swallowed them.
I was like, whose birthday were
Yeah, I'm just gonna tell you.
No one used to be the crazy.
No.
Dude, okay, then you posted?
Except for English. In English, I do. I'm always sick of
I don't remember taking this picture. I may look a little bit nervous. I am.
I used to have.
You guys looking next 20 minutes and that guy's like, he's doing it. Right here. This was.
Oh yeah.
It's a good, it was a good time.
Okay, focus your attention up at the front, please. So, question 3A is basically saying calculate the standard molar enthalpy of combustion for the substance that's reacting with oxygen. So, the symbol that we're going to use every single time is standard, the little not symbol, that's just under standard conditions. So standard molar enthalpy of combustion, and it's a change in enthalpy, right? What is molar enthalpy always measured in? Kilojoules per mole. You can do every single one of these questions by unit analysis. Every single one of these questions can be performed by unit analysis. Do you have anything related to kilojoules or moles? Yeah. What? Kilojoules. How many kilojoules in this reaction? What is it? 114. Is it positive or negative?
Actually,
It's negative. Why is it negative? Because it's on the product side. Good. So negative 114 kilojoules. And how many moles of my hydrogen gas are reacting to do this? 2. 2. How did you get that? That's the coefficient in front of that substance, right? So 2 moles of hydrogen are reacting in order to produce negative 114 kilojoules. So if we take that and divide it by 2, we should get 57.
Yep.
Negative 57 kilojoules per mole. Should be 0. What?
my bad. I used the wrong coefficient. I was looking at question 3 and nothing about everything. What's going on?
483.6. Okay, thank you for bringing that to my attention. 483.6. Oh man! Holy guacamole!
Oh,
483.6. That's my fault. That's 100% my fault.
I was looking at the
Woo. Okay. So we want the molar enthalpy of combustion. Are we for sure done? Okay, good. We want the molar enthalpy of combustion for this reaction. It's negative 483.6 kilojoules for every 2 moles. And then we divide that. It's going to be 236.8.
241.
Oh, 241. Negative 241.8 kilojoules per mole. Okay, does that make sense?
Yes.
Yes, we're just using unit analysis to get the molar enthalpy for this reaction. So if we were to look at question 3b, it's the same thing. Molar enthalpy of combustion, so kilojoules per mole is what we're looking for. And if we have negative 1272.1 kilojoules, and how many moles are reacting to produce this much energy? 4. So I can't do that in my head. It's going to be 318.
18.025.
318.03 kilojoules per mole. Sure, negative, perfect. So is this fairly straightforward? Yes. What's the answer for C?
81.6.
What?
Positive 81.6, right? Yeah. So we're going to get positive 81.6 kilojoules per mole. And then D, negative 372.8. Negative 372.8 kilojoules. I don't know, hopefully kind of we're all on the same page right now. All we're doing is we're trying to convert between the types of enthalpy, of ways we can communicate enthalpy. That's all we're doing. So we're trying to go from either the delta H notation or when it's a product or a reactant, and we're just trying to give somebody a molar enthalpy of combustion. Question number 4. What is the enthalpy change for this reaction? Are we gaining or losing energy? We're losing, and how much are we losing? 114. So if I were to ask you for A, what is the enthalpy change? I would say we are losing 114 kilojoules. I would actually write that out as a sentence. But then for B, I don't think I can write on this. No, I can't. But then for B, it says write the chemical equation using delta RH notation, not under standard conditions. So what that means is it wants me to rewrite the entire reaction, blah, 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 blah. But the enthalpy of the reaction is going to be negative 114 kilojoules.
That's it.
That's it. That's all B is asking you to do. It's just asking you to rewrite the entire equation, then use delta RH notation. That's it. It's. I don't really understand what they're getting at between A and B, but that's fine. Whatever. Then it says calculate the molar enthalpy of neutralization for sulfuric acid. How many moles of sulfuric acid are used in this reaction? 1. So it's this divided by 1, right? So the molar enthalpy is going to be, molar enthalpy of neutralization is going to be negative 114 kilojoules over 1 mole. So negative 114 kilojoules per mole. Yeah. How many moles of sodium hydroxide do we use? 2. So is the molar enthalpy for the sodium hydroxide going to be the same thing? No. The molar enthalpy of neutralization for the sodium hydroxide is going to be negative 114 kilojoules per 2 moles. So then it's going to be negative 57 kilojoules per mole. So we've got 2 different molar enthalpies, but that's because we need 2 different chemical amounts to do this chemical reaction. Does anybody have any questions about that? Is it more clear now than it was on Friday?
Yes.
Okay, well that's the goal of today, right? The goal of today is just to make sure we're all on the same page. And then 6A, B, C. Give me a second to erase this. Propane obtained from natural gas is used as a fuel in barbecues. We already did that one, right?
Yeah.
So we'll do D or B. Nitrogen monoxide forms at high temperatures inside automobile engines. Can somebody tell me the key word in 6B? Forms. That's a formation reaction. So we're making nitrogen monoxide. And so what 2 elements do I need in order to make nitrogen monoxide? Nitrogen and oxygen gas. Now there's 2 ways to do this, right? There's 2 ways to balance this reaction. What do you want to do? Do you want to do it the way we always do it, or do you want to do it the way that we never do it?
Let's do the opposite.
No.
We do the never way.
No.
The never
Oh, we're
way.
doing it the other way.
What was the other
No,
Yes.
it's like what do you No, we're not doing half. That can burn. I don't like it. Oh shit. I hate fractions. I hate fractions. I hate fractions so much.
You hate fractions. Fractions are just tiny numbers. That's all they are.
I like
Whatever.
big numbers.
Okay. What I want to ask you is for the very first reaction, do you immediately know what the enthalpy of this reaction is going to be? Yes, you do? What is it? Okay. For the enthalpy of the second reaction, do you immediately know what the enthalpy is?
Yes.
I do.
Same thing.
I know. How many moles of nitrogen monoxide absorb 91.3 kilojoules? 1. For every 1 mole of nitrogen monoxide, we absorb 91.3 kilojoules. For what's our coefficient here? 1. So for every 1, we absorb, what was that number, 91.3?
Yes, sir.
91.3 kilojoules. For every 1, this is how much energy we absorb. Okay? Now, for the top reaction, You can use your intuition or you can use unit analysis. What do you want to use, intuition or unit analysis? Okay, so what number is going to go here? Double that. Okay, that's your intuition, right?
Yeah.
Let's double check using unit analysis.
Whoa.
Funny. Jokes.
I'm laughing so hard.
Denver, what is enthalpy measured in?
Funny kg.
Funny.
That's about right.
Thank you very much. Denver, yes, absolutely. Enthalpy is measured in kilojoules. So enthalpy measured in kilojoules. Do you have anything related to kilojoules here?
Yes, sir.
Yes, per 1 mole, right? So positive 91.3 kilojoules for every 1 mole of nitrogen monoxide. How many moles of nitrogen monoxide do we have in this reaction? We have 2 moles of nitrogen monoxide. So that means we're going to need 182.3 kilojoules. So we would put positive 182.3 kilojoules. Yep, totally would. Thank you. I really appreciate it. Thank you for not judging me. Okay, good. Thank you for judging me, but at least keeping it silent, using your internal voice. Some advocates for alternative fuels have suggested that cars could run on ethanol. So the very last thing we're going to do is we're going to write this reaction. Did anybody balance this reaction?
No, I gave up.
What was the coefficient on the ethanol that you got? 2. So C2H5OH. When I burn something, what do I react it with? And what do I always make?
Carbon dioxide and water.
Carbon dioxide and water vapor. Okay. 2 carbons. 2 carbons. How many hydrogens? 6. So I need a 3 here. How many oxygens on this side? I see 3. Yeah, I know. How many oxygens on this side? 7. So we don't want to change this coefficient yet, because if we change that, then the other ones have to change as well. So how can I make 7? If I ignore this one, what do I have to add? What total amount of oxygens do I need here in order to add to 1 to get 7? 6. So we'll toss a 3 here. We didn't need that 2 out in front, and I think the only reason why is because you missed that one. Yeah. Okay. So is my energy going to be a reactant or a product? It's going to be a product, and we've seen this reaction already today. Positive 124. 1, 2, 3, 4.8 kilograms. We saw this right here. The burning of ethanol, and it gave us an enthalpy of that. So, what I want to ask you is, do you kind of feel more prepared?
Yes.
Okay. Tomorrow we're going to do a lab. And then after that, we're going to, I'm going to give you some more practice problems probably. You're going to have a quiz on Wednesday. I'm going to tell you right now, your quiz on Wednesday is going to be 11.1 to 11.2. So everything we've done up to until now. The notes are all up on Google Classroom, so you can check that out.